Okay, let's unpack this. Welcome back, everyone, to the deep dive. In the, well, ever-evolving world of large language models, data isn't just king. It feels more like the entire kingdom, right? The very bedrock.
Absolutely. It's everything.
The capabilities, the intelligence, if you will, of an LLM are just so directly tied to the sheer volume and maybe more importantly, the quality of data it eats up during training.
That quality piece is key. You can have tons of data, but if it's low quality.
Exactly. But here's the persistent problem, the sort of foundational challenge. How do we actually get enough truly high-quality data, especially when, human annotation is notoriously slow?
Oh, incredibly slow.
Yeah.
And expensive.
So expensive. And sometimes, even with the best intentions, it can be prone to its own subtle biases.
Yeah, that's a real issue, human variability.
This isn't just a small hurdle. For many projects, it really feels like the main bottleneck. It dictates how fast we can develop and deploy these incredibly powerful models.
It really does. It gates the progress in many ways.
So today, we're embarking on a deep dive into a really groundbreaking method that tackles this challenge head-on. It's called CoT-Self-Instruct.
Right. CoT chain of thought.
And this isn't just about feeding LLMs more data. That's maybe the old way. This is about teaching them to generate better data, on their own.
Autonomously. Yeah.
And then, and this part is maybe even more remarkable, equipping them with the tools to self-curate that data, to make sure it's genuinely top-tier stuff.
That self-curation is fascinating. A quality control loop built right in.
It's a huge leap forward, really. It shows how these models aren't just passive consumers of information anymore. They're evolving into sophisticated creators and pretty rigorous curators of their own learning material.
What's truly fascinating here, I think, is how this method gets right at that fundamental, persistent challenge in LLM development. The reliance on these massive, high-quality data sets, it cleverly leverages the very models we're trying to improve the LLMs themselves to generate the data needed for their own training.
Using the tool to build the tool.
Exactly. But, and this is crucial with a really strong emphasis on explicit reasoning, that chain of thought part, and then that rigorous quality control you mentioned.
Right.
So it's not just volume for volume's sake. It's about the strategic, intelligent generation of highly effective training signals. It feels like a shift from just data acquisition to something more like intelligent data creation.
Intelligent data creation, I like that. So our mission today, as always on the deep dive, is to cut through the complexity. We want to extract the core technical details and really understand the far-reaching implications of this approach.
Get into the nuts and bolts.
Exactly. We're going to try and illuminate exactly how LLMs are being taught to, well, think about generating their own training data. What does that thought process actually look like under the hood? And critically, why is this leading to such significant performance gains across different kinds of tasks? We'll dig into the mechanics, the metrics, and what this whole paradigm shift could mean for the future of AI training.
Yeah, focusing on the technical breakthroughs, the engineering side of it.
Precisely. We'll keep our focus squarely on the tech and the engineering ingenuity involved here. So, large language models, they have, without a doubt, truly transformed the landscape of deep learning. They've unleashed capabilities that, honestly, just a few years ago felt like pure science fiction.
It's been incredibly rapid progress.
But their immense power, as we've kind of alluded to, is just inextricably tied to the sheer volume and maybe even more importantly, the quality of data they're trained on.
Can't emphasize that quality aspect enough.
It's like this insatiable appetite for good, clean, relevant information. Without it, even the most sophisticated model architecture would just, falter, like a high-performance engine trying to run on bad fuel.
That's a great analogy. And if we connect this to the bigger picture, the rapid advancements we've seen, and you see this reference constantly in the literature, recent papers from researchers like Zhang, Guo, Long, just this past year.
Right, 2024 has been busy.
It's all deeply rooted in their ability to scale.
Yeah.
And that scaling, that relentless drive for bigger and more capable models, fundamentally relies on these vast, high-quality data sets.
It's the foundation.
It really is. It's not a minor detail. It's a core principle governing LLM development. As folks like Gandhi and Abdin highlighted in their 2024 papers, the big success stories we see with recent LLMs, they're directly linked to innovations in how we get, process, and use training data. Without a continuous, high-fidelity supply of diverse, clean data, that upward performance curve, which has honestly surprised even us sometimes.
Yeah.
It would inevitably flatten out. That hunger for data is palpable, and it's a primary driver behind so much of the current research into making data pipelines more efficient and effective.
So to feed this insatiable hunger, historically, we've leaned really heavily on human-annotated data.
Right, the traditional way.
Human experts meticulously labeling things, categorizing, crafting examples for models to learn from. It was, and maybe in some areas still is, kind of considered the gold standard.
For a long time, yeah.
But that traditional approach comes with some really serious, very practical hurdles. What are those big challenges that make human-generated data such a bottleneck, even if it's perceived as high quality?
Indeed. And they are significant hurdles. Acquiring human data at the scale needed for today's LLMs is often just plain impractical. There are a few big reasons.
Okay.
First, the cost. It's prohibitively high. Human labor, especially for specialized tasks needing real domain expertise, is expensive, and it just doesn't scale linearly with the exponentially growing data demands of LLMs.
Right, training a new model could mean millions of examples.
Exactly, millions. The cost quickly becomes astronomical, limiting who can even attempt it.
Makes sense. What else?
Second, data scarcity. It's a very real problem, especially in highly niche or maybe emerging domains where human expertise is just rare. You simply can't find enough experts globally to generate the sheer volume needed for every obscure scientific field or specialized technical application.
Never enough experts.
And then you've got significant privacy concerns that come into play. Researchers like Kirkin pointed this out back in 2023.
Right. Sensitive data.
Exactly. When you're dealing with personal information, proprietary business data, classified research, that data often just cannot be freely annotated or shared, which creates these massive gaps in potential training material.
Okay, cost, scarcity, privacy, those are big practical barriers.
They are. But beyond those, several critical studies, folks like Hosking, Singh, Ghilardi, also in 2023, have consistently shown that human-generated data isn't always the ideal, even when you can get it.
Oh, interesting. How so?
Well, it can be prone to inherent biases and inconsistencies. Human annotators, even with the best intentions and rigorous guidelines, inevitably bring their own perspectives, their own understanding, their cognitive shortcuts to the task.
Unconsciously, maybe.
Often unconsciously, yes. This can inadvertently introduce subtle subjective biases, inconsistencies in how labels are applied, or even just outright errors. And when you scale that across millions of data points, it can really negatively impact a model's ability to generalize robustly or even stay objective.
Wow. So the gold standard isn't always so golden.
It raises a really important question for engineers and developers. Can we truly trust the quality, the objectivity, and frankly, the scalability of human labels enough for the next generation of models? Especially these large-scale, high-stakes models that need precise, unbiased reasoning.
Right.
It's a fundamental challenge pushing us, pretty urgently, to look for more scalable and, crucially, more controllable alternatives.
Okay, so given these pervasive and complex challenges with human data, the cost, the scarcity, privacy bias, it's really no surprise that synthetic data has emerged as this, viable and increasingly intriguing alternative.
It makes a lot of sense.
It's essentially data that's artificially generated to mimic real-world data characteristics, but crucially, without the direct constraints of human labor.
Right. Scalability on demand, potentially.
It offers this promise of maybe unbounded scalability and a level of precise control that human annotation often just inherently lacks. Seems like a very logical next step.
Absolutely. And synthetic data generation isn't just one thing. It involves a whole range of increasingly sophisticated methods. The field is moving incredibly fast.
Okay.
At one end, you have sort of traditional algorithms using programmed rules to create data points based on predefined parameters, useful for simpler structured stuff. Then more recently, you have these advanced generative models, think GANs, generative adversarial networks, or variational autoencoders. Folks like Borisov and Meng explored these back in 2022. These models learn the underlying statistical patterns of real data.
And then generate new examples.
Exactly. They produce new, statistically similar examples, effectively fabricating data points that closely resemble the real thing, but are entirely synthetic. And beyond that, complex simulations are becoming huge. Vesnovet showed some powerful examples in 2023. Think about training self-driving cars in virtual worlds.
Right. Generating endless scenarios.
Exactly. Or creating diverse training sets for robots in a simulated factory. These are incredibly promising, where real-world data is just too hard, maybe too dangerous, or too expensive to get at scale.
Or too sensitive, like you said before.
Precisely.
Yeah.
The grand promise of synthetic data is this potentially unbounded source of training material, provided its quality can be rigorously controlled and validated. And that control, that validation, is exactly where the latest innovations, like the one we're discussing today, are really focused.
Okay, so within this burgeoning world of synthetic data, the original self-instruct method, pioneered by Wang and others back in 2022, that was a genuinely big step, wasn't it?
It really was foundational.
It allowed LMs to essentially generate their own instruction-following examples. How did that original method work at a high level? What was the core mechanism?
So, Self-Instruct essentially bootstraps the data generation process. It leverages the LLM's own ability to generate text. You start with a small, but very carefully chosen set of seed examples.
Okay, like starting points.
Exactly. Think of them as a handful of high-quality questions paired with their desired answers or responses. These seeds are then fed to the LLM as few-shot examples within a larger prompt, and that prompt instructs the LLM itself to produce additional new demonstrations in a similar format. It's kind of like giving an LLM a few perfect examples of math problems.
It has to get to make more math problems.
Precisely. Make more original problems based on those examples. The model learns the style, the structure, the type of instruction from those seeds, and then tries to replicate that by creating new original instructions. The brilliance of that initial approach was realizing the LLM itself could be an active participant in the data pipeline, not just the end consumer. That really changed the game for data acquisition.
And since that original paper, we've obviously seen a number of variants building on that idea, right? Pushing the boundaries of what self-instruct to do.
Absolutely. The research community jumped on it, they recognized the huge potential, and subsequent work quickly focused on refining and improving it in several key areas.
Like what?
Well, some variants, like those from Liu and Zhang more recently, focused on significantly increasing the complexity of the generated queries, making them harder, more nuanced, less trivial.
Okay, raising the bar.
Others, like Ding's work, focused on maintaining semantic diversity, making sure the synthetic data covered a wide range of topics and instruction types, not just variations on a narrow theme.
Preventing it from getting repetitive.
Exactly. Scaling data generation was another big goal. Yuan and others looked at producing even larger quantities efficiently. And maybe most fascinatingly, we saw early forms of self-improvement loops. Yuan explored this in 2024, where the model doesn't just generate data, but iteratively refines its own data generation process.
Wow, becoming a better teacher to itself over time.
Kind of, yeah. But even with all these advancements, a core technical challenge kept popping up, consistently ensuring the quality and the actual effectiveness of the generated data for training, especially for complex tasks.
The quality problem again.
Great. While these methods could pump out volume, the underlying quality, the guarantee that this data would genuinely make the model better at, say, complex reasoning, that wasn't always optimal or consistent. And this is a crucial point the paper we're diving into today really hammers home. Generating truly high-quality synthetic data and, just as importantly, optimizing its use for both reasoning and non-reasoning tasks still remains insufficiently understood.
So it's not just about making data, but making data that truly makes the model smarter, especially for harder stuff.
Exactly. Smarter in a measurable, robust way, particularly in domains needing deeper cognitive abilities, not just surface pattern matching.
Okay, this brings us perfectly to CoT-Self-Instruct. As you've set it up, it directly tackles that very quality challenge. It's an evolution, building on self-instruct, but adding some really crucial layers of ingenuity. So, what are the two core technical innovations they're proposing? What makes this a breakthrough?
Right. This method introduces two key technical components that really set it apart. It's a significant conceptual leap, I think. First, it explicitly integrates chain of thought, that CoT reasoning, directly into the data creation process itself.
Okay, embedding the reasoning.
And it's not superficial. It means the LLM isn't just spitting out prompts directly. It first engages in a much deeper, multi-step reasoning and planning process about how to generate those prompts.
Like thinking before speaking, but for prompt generation.
Kind of, yeah, like planning an essay before writing. Second, it incorporates a really robust self-filtering mechanism. This is designed to automatically curate only the highest quality synthetic data.
The quality gate.
Exactly, ensuring only the most effective, most reliable examples get used for training. training. And the power of this combination, deliberate generation plus meticulous self-curation, is then rigorously demonstrated across both verifiable reasoning tasks.
Where you know the right answer.
Right. And non-verifiable general instruction following tasks, which are more open-ended, more subjective. That blend of intelligent generation and automated curation is what makes it so potent.
That sounds like a powerful combination. Let's really dive deep now into how the generation works. It starts, like the original, with seeds instructions. But how exactly does adding chain of thought make the LLM's prompt generation fundamentally different and, better? What's happening under the hood?
Okay, so unlike standard self-instruct, which often prompts the model fairly directly, here are examples, give me more like this, CoT-Self-Instruct takes a much more deliberate, almost transparent approach.
How so?
The LLM is first shown an n-shot set of sample instructions, those seed examples. But here's the crucial step. Before it generates anything new, it's explicitly prompted to carefully analyze these seeds.
Analyze them, not just copy them.
Right, analyze them deeply, identify their underlying domain, assess their complexity, recognize recurring patterns, understand their core purpose. It's actively deconstructing the examples, like an expert reverse engineering a problem set.
Okay, so it's learning about the examples first.
Exactly. And only after that thorough analysis, after reflecting on what makes these seed prompts good, maybe spotting optimal structure, certain question types, the reasoning steps needed only then is the LLM prompted to reason step by step to come up with a plan for generating a new instruction.
A plan, so it outlines it first.
Yes, a comprehensive plan. This detailed plan then guides the final output, ensuring it meets similar quality and complexity requirements and sticks to a strict format. For instance, for a math problem, the plan might outline the type of equation, number of variables, expected solution format.
And for, say, a creative writing prompt?
It might detail the genre, required story elements, target audience. This explicit pre-computation of a plan, this thought process, is what dramatically elevates the quality and coherence of the generated instructions. It moves beyond simple imitation to structured, intentional creation.
So if getting this right, it's like the LLM becomes its own internal prompt engineer, meticulously planning and designing its instructions before writing them. That sounds like a much deeper level of metacognition than just pattern matching.
Precisely. That's a fantastic way to put it. This pre-computation, this thought process is absolutely key. It shifts the LLM from being a simple generator to a deliberate designer. Now, for verifiable reasoning tasks, think math, logic puzzles, things with a definite right answer.
Where you can check the work.
Exactly. The LLM is instructed to generate both the new instruction and its verifiable target answer. This is critical for the whole pipeline.
Oh, it solves its own problems.
Yes. For example, given math problems as seeds, it might generate a new question like, find the value of k such that the system of equations kx plus y equals 1 and x plus k equals 1, 1 has infinitely many solutions. And then it will solve it itself using internal reasoning steps to provide the final boxed answer, like boxed 4.
Wow.
This self-contained generation of both problem and solution is vital for the filtering stage leader, providing a model-generated ground truth for self-validation. It's not just creating a problem, it's showing it can solve it, setting its own benchmark.
That interplay of problem generation and self-solving is brilliant for verifiable tasks. But what about those more open-ended instructions, general instruction following, where there isn't just one right answer to box up? How does CoT-Self-Instruct handle those?
Good question. You're right, that distinction matters. For those open-ended tasks where a single correct answer isn't generated during beta creation, the LLM generates only the instruction, not a response.
Okay, just the prompt.
It's just the prompt. But the template for these tasks still demands that robust three-step CoT process. First, identify common elements and principles in the seed prompts. Second, develop a comprehensive, detailed plan based on those elements outlining the desired characteristics, scope, complexity of the new prompt. Third, execute that plan to provide the final synthetic prompt.
So the planning is still there.
Absolutely. An example they give is generating a create a suggestion for the Meiji Shrine to incorporate digital elements into New Year festivities. The thinking here is that for these open-ended tasks, the quality of the response to that instruction will be assessed later by a separate reward model.
Ah, so the response quality is handled downstream.
Exactly. It eliminates the need for a reference answer at the generation stage, streamlining things for subjective tasks while still fully leveraging CoT planning. It's a practical design choice, separating the concerns of instruction generation and response evaluation, much like in RLHF pipelines.
Makes sense.
And one more technical detail in this creation stage, ensuring domain specificity. to avoid generating weird, unnatural prompts like mashing up philosophy and coding.
Right, that wouldn't be helpful.
The method proposes first categorizing the seed prompts into distinct domains. Then, during few-shot prompting, the LLM only samples seeds from the same category.
So math seeds lead to math prompts, story seeds to story prompts.
Precisely. It acts as a constraint, guiding the LLM to generate more relevant, coherent, and ultimately more useful training examples within established themes. It maintains naturalness and prevents those bizarre cross-domain prompts that would just confuse the model during training. It's subtle, but really vital for practical data quality.
Okay, so the LLM generates a bunch of prompts using CoT to make them inherently better. But as you said, not every single one will be perfect, even from a smart generator. So the next critical piece, and arguably one of the most ingenious parts, is how they ensure only the absolute best of this self-generated data makes it into the training set. What's this survival of the fittest mechanism?
This curation step is absolutely crucial. You framed it perfectly. Because, yeah, even with powerful LLMs planning things out, not every generated instruction will be perfectly well-defined, answerable, or optimally effective for training. It really is about survival of the fittest prompts to make the training data as clean and impactful as possible.
Right.
Now, for verifiable reasoning tasks, where we have that clear ground truth answer, the LLM generated itself.
The one it solved earlier.
Exactly. They introduced this novel and really effective filter called answer consistency.
Answer consistency. Okay, that sounds like a twist on the self-consistency method we've seen elsewhere. How does it work? How is it different from just generating multiple answers and taking a majority vote?
You're right to spot the connection and the key difference. With answer consistency, the LLM first generates K responses. They use 16 in their experiments for a given task. Then it identifies the majority response among those K solutions.
Okay, standard self-consistency so far.
Right. That part assumes the most frequent answer is likely correct. But here's the critical differentiator, the extra layer of filtering they talk about. It then rejects the synthetic data example if this majority response does not match the target answer that was originally generated by CoT-Self-Instruct during the instruction writing phase.
Ah, it checks against its own original answer from the planning stage.
Precisely. Remember, that original target answer was produced with extensive CoT reasoning, serving as the LLM's own gold standard for the problem it created. This comparison provides an incredibly powerful filter, shown to be much better than standard self-consistency, which just looks for internal agreement among new solutions.
So it's like the LLM sets its own test, takes the test multiple times, and if the class consensus doesn't match its original answer key, it throws out the test question entirely.
That's a perfect analogy. That level of self-scrutiny ensures exceptional quality. The checkmark and no entry sign visuals in the paper really capture this accept-reject mechanism based on that specific internal consistency check.
Brilliant. Okay, but for the non-verifiable tasks, general instruction following, where there's no single right answer, answer consistency wouldn't work there. How do they filter those?
Exactly. Answer consistency isn't applicable there. So instead, they employ the rejecting instruction preferences, RIP method. This was proposed relatively recently by you and others.
RIP filtering. Okay. How does that work?
It's clever because it leverages reward models. For a given instruction, the LLM generates K responses again, multiple attempts to follow the instruction. Each of these K responses is then evaluated by a pre-trained reward model, an RM.
Which scores the quality of the response.
Right. The RM assigns a numerical score indicating how good the response is, how well it followed the instruction according to its learned preferences. The filtering process then selects prompts that consistently lead to higher scores.
How does it define consistently higher?
Specifically, they use the lowest score among the K responses to represent the synthetic prompt's overall quality. This is quite strict.
So if even one response is bad, the prompt might get rejected.
Essentially, yes. It heavily penalizes prompts that lead to even a single low-quality response among the attempts. This pushes for overall reliability and high average quality across all potential responses to that prompt.
I see. The bar charts in Figure 1 probably show this.
Exactly. Example by 1 is selected because its responses generally get higher reward scores compared to by 2 or by 3, which likely had at least one low-scoring response. It effectively filters out prompts that consistently confuse the model or lead to poor outputs according to the reward model's judgment.
Ensuring the training data really pushes the model towards preferred behaviors.
Precisely. And it's worth really emphasizing, this filtering step, whether it's answer consistency or RAP, consistently provides further significant performance gains, even if it means reducing the total amount of training data.
Quality over quantity.
Absolutely. It underscores that critical point the paper makes repeatedly. Quality over quantity is paramount in synthetic data training. It's not about having the most data, but the most effective and clean data. This aligns perfectly with findings elsewhere suggesting smaller, meticulously curated datasets can outperform massive, noisy ones. It's powerful validation.
Okay, so they've generated this data with CoT planning, then meticulously curated it with either answer consistency or RIP. Now they have this high-quality synthetic data set. How is it actually used to train the LLMs? What's the self-training methodology?
Right. The selected synthetic instructions become the fuel for reinforcement learning, or RL training. This is a powerful way to fine-tune LLMs based on feedback.
Okay.
The specific RL algorithms they use differ based on the task type, chosen for how well they fit the kind of feedback available. For reasoning tasks where answers are verifiable and you have a clear correctness signal. Exactly. They use GRPO-guided reinforcement learning with rule-based verifiable rewards. Think of GRPO as an RL method specifically built for learning from clear, unambiguous, often binary feedback. Perfect for math or logic where correctness is precise.
Makes sense. And for the general instruction following, the more subjective stuff.
There, they compare two main approaches: offline DPO, direct preference optimization,
DPO, okay.
and online DPO, which often performs better, as Lanshanton and others discussed recently. DPO methods learn directly from comparing preferred and dispreferred responses. The offline version uses a fixed dataset of these preferences, while online DPO iteratively collects new preferences and updates the model.
You get more dynamic.
Yeah, more dynamic and often better suited for open-ended generation where quality is nuanced and judged by preferences.
Got it. So they're testing both generation and curation across different task types using appropriate RL methods. That sounds incredibly thorough. What specific models and data sets were involved in these experiments? How did they set up these tests?
They were indeed thorough. For the reasoning tasks, the initial seed instructions, those starting points, came from the S1K dataset. Specifically, a subset of 893 verifiable reasoning prompts from S1K that consistently give simple, checkable answers like single numbers or simple formulas.
A clean starting point for verifiable CoT.
Exactly. The prompt generation models were based on Qwen 3.4b. They used the base model, but also variants with think mode enabled for CoT generation and no think mode as a baseline to directly measure the CoT impact.
Clever comparison.
They also use specific generation settings, temperature 0.6, top P 0.95 to control the creativity versus predictability of the output, fine-tuning the randomness and diversity.
Standard practice, but important details.
Very important. Training always started from the Qwen 3.4b base model, and evaluation used a tough suite of math and reasoning benchmarks: Math 500, AIM 2024, AMC 23, and GPQA Diamond. The metric was average accuracy over 16 generated solutions per problem, giving a robust measure of reasoning skill.
Okay, solid setup for reasoning. What about non-verifiable instruction following?
There, the seed prompts were 4,000 high-quality examples from WildChat RIP filtered by 8B Llama. And crucially, these were carefully categorized into 8 distinct domains.
Like writing and storytelling, technical and programming.
Precisely. That categorization, as we discussed, ensures few-shot sampling keeps things coherent and avoids those weird cross-domain prompts. The generation model itself was Llama 3.18b Instruct, a strong baseline. And for the RIP filtering step, they used the Athena RM8b reward model, specifically trained for quality assessment.
So specific models, curated seeds, standard benchmarks, it all sounds very rigorous.
It really does. The meticulous choices make the results highly credible.
You mentioned DPO training for those non-verifiable tasks. Were there any specific technical hurdles or subtle challenges they had to tackle during that DPO process, especially given how subjective those tasks can be?
Yes, they hit an interesting and actually quite common technical challenge with DPO for these open-ended tasks: the tendency for evaluation judges, especially reward models, to implicitly favor longer responses.
The length explosion problem, where longer answers get higher scores just for being long.
Exactly. Models can learn that just producing more text often gets a better score from the RM, even if the text isn't actually higher quality, more concise, or more useful.
Which isn't always what you want.
Definitely not. So, to mitigate this, they adopted a clever approach from Wu and others from 2024. It involves combining the reward score with length information when determining the preferred response. They used a specific length normalization coefficient, 0.2 in this case.
So it balances quality score with brevity.
Essentially, yes. This adjustment ensures shorter, high-quality responses aren't unfairly penalized just because they're shorter than verbose, less efficient ones. It helps maintain conciseness when quality scores are similar, promoting a better trade-off between being informative and being succinct.
Which is often crucial for real-world use.
Absolutely. But this technical fix for length bias does raise a deeper, quite interesting question that the paper doesn't fully explore but is really relevant.
Oh, what's that?
Well, why do LLMs tend towards longer responses, and why do reward models often prefer them without being explicitly told to? Is it just a superficial thing where more text means more chances to hit keywords the RM likes?
Or something deeper.
Or is there maybe an implicit bias towards verbosity embedded in the huge amounts of human text these RMs learned from in the first place? And critically, how much does this length bias actually affect real-world usefulness? Often, you want concise, accurate answers, not just long ones.
That's a fascinating point. Understanding why it happens is key to fixing it properly.
Exactly. Understanding and countering this bias is a big area of ongoing research into how models can subtly misinterpret our goals.
All right, let's get to the numbers. The proof is in the pudding, as they say. How did CoT-Self-Instruct actually perform on those tough reasoning tasks compared to the old ways in human data?
Okay, the results for reasoning are pretty striking. They really showcase the technical advantages, just looking at the raw output before any
It's
filtering.
just code generation versus standard self-instruct generation.
Right. CoT-Self-Instruct achieved an average accuracy of 53.0%. Standard Self-Instruct was at 49.5%.
Okay, a clear win for code generation right off the bat.
A clear win. It immediately shows the benefit of that chain of thought playing during generation. The raw material is just better.
But the filtering should help even more.
Hugely. So, applying standard self-consistency filtering bumped Self-Instruct up to 53.6%. Respectable gain. But CoT-Self-Instruct with that same filter went higher to 55.1%.
Still ahead.
Still ahead. Using RIP filtering, Self-Instruct got to 54.5%, but CoT-Self-Instruct reached 56.2%.
There again.
And then the optimal filter, their novel answer consistency.
The one checking against its own original answer.
That one pushed CoT-Self-Instruct to an impressive 57.2% average accuracy, using about 2,900 curated training examples. This systematic improvement with filtering just powerfully drives home that quality over quantity point. Strategic curation really amplifies the gains from CoT generation.
Okay, 57.2% sounds good.
Yeah.
But how does that compare to using actual human-annotated datasets? Or the supposed gold standard?
This is where it gets really interesting. Models trained on this filtered CoT-Self-Instruct data significantly outperformed models trained on existing human datasets.
Significantly.
Yeah. That 57.2% accuracy with CoT-Self-Instruct answer consistency filter, 2,926 examples, is way higher than the 44.6% they got from training on the original S1K prompts, 893 examples.
Wow, that's not a small difference. That's huge.
It's a massive leap. And here's maybe the kicker. Even when they match the training data size filtering CoT-Self-Instruct down to just 893 examples, same as S1K.
To make it apples to apples on size.
Exactly.
Yeah.
CoT-Self-Instruct with answer consistency still achieved 54.2%.
Still way better than the 44.6% from the human data at the same size.
Demonstrating a substantial quality advantage, per example. It's not just volume. Furthermore, it significantly beat training on 10,000 open math reasoning instructions, which only got 47.5%, showing sheer volume from other synthetic sources isn't enough. And when they increased their own CoT-Self-Instruct data to 10,000 examples with answer consistency, the average accuracy went even higher to 58.7%. It just hammers home.
Yeah.
It's smarter, deliberately generated, rigorously curated data that makes the difference.
It really does seem like the combination of code planning and smart filtering is the key.
Which raises that deeper question again. What is it about that reasoning and planning phase in CoT that makes the generated prompt itself inherently higher quality, even before filtering?
Yeah, why is the raw output already better?
Is it just creating more complex prompts that push the model harder? Or is it that the planning makes the prompts more trainable somehow? Maybe they're structured in a way that just clicks better with the RL process, making learning more efficient.
Better structured for learning.
The paper shows the effect clearly, but the precise mechanism for that pre-filtering quality boost, that trainability factor, that's a fascinating area for more research. Could unlock even better generation strategies.
Absolutely. Okay, that's a massive win for reasoning tasks. A really compelling story there. What about the non-reasoning general instruction following tasks? Did CoT-Self-Instruct also shine there, where evaluation is more subjective, relying on reward models?
Yes, very similar and equally compelling trends emerge there too. It confirms the approach is robust across different task types and evaluation methods.
Good to see that consistency.
So for non-reasoning tasks, CoT-Self-Instruct got an average of 53.9% without any filtering. Again, substantially better than original Self-Instruct's 47.4%.
Reinforcing that code generation helps even for open-ended stuff.
Definitely. And the paper specifically notes, this is interesting, that asking for longer CoT reasoning chains during prompt generation led to even greater gains. You can see that in an appendix table. It further emphasizes the value of explicit, detailed, thorough reasoning for producing top-notch synthetic data.
More thinking leads to better prompts. Makes intuitive sense.
It does. Yeah, RIP filtering also proved effective here, boosting CoT-Self-Instruct from that 53.9% baseline up to 54.7%. A nice incremental gain, showing curation still helps even on strong data.
Okay.
Interestingly, though, RIP filtering gave an even bigger boost to the human-generated prompts from WildChat. It took them from 46.8% up to 50.7%.
Huh. Why would filtering help human data more?
The paper suggests it's because the human data was relatively noisy compared to synthetic data, which makes filtering even more critical for it.
So the CoT-generated data started cleaner.
That's the implication. It highlights a subtle but important point. Carefully controlled machine-generated data, especially with CoT planning, might have a higher baseline quality and consistency than typical human annotation with all its inherent variability. Synthetic data here shows tremendous promise for scaling high-quality, consistent training signals.
Fascinating trade-off. Okay, and the overall performance against human data for these non-verifiable tasks. Head-to-head, how did the best CoT-Self-Instruct model fare?
All right, the best DPO-trained model using CoT-Self-Instruct with RIP filtering achieved that 54.7% average score on benchmarks like AlphaGeval 2 and ArenaHard.
Okay.
This significantly outperforms training directly on the raw human prompts from WildChat, which only got 46.8%.
Big difference again?
And even when those human prompts were also filtered with RIP, they only reached 50.7%, still noticeably below the CoT-Self-Instruct data.
So the synthetic pipeline won out?
Clearly. It demonstrates that the whole pipeline intelligent generation plus rigorous curation produces training data that leads to superior instruction-following models better aligned with user preferences as judged by these benchmarks.
And did they try online DPO?
They did, and when they moved to online DPO training, which, remember, is more dynamic,
Right, adapts more quickly.
the performance gap widened even further. CoT-Self-Instruct plus RIP achieved an impressive 67.1% in that setting, compared to human prompts, 63.1%. It just comprehensively confirms the robustness and effectiveness of this synthetic data approach across different training methods. It consistently produces high-impact training data that translates directly into better model performance.
This is where the implications really start to sink in, isn't it? What we've seen in this deep dive feels like a truly remarkable technical achievement.
It really does.
CoT-Self-Instruct isn't just about, throwing more compute at data generation. Not at all. It's about leveraging the LLM's own reasoning capabilities to strategically design higher quality training data.
Like becoming its own curriculum designer.
Exactly, like a self-aware curriculum designer, and then rigorously self-curating it through these clever automated filters. This feels like a monumental shift in how we approach the fundamental scaling challenge in AI.
It truly represents a significant paradigm shift, I agree. By instructing LLMs to first plan and reason to actually think about the prompt generation process, analyze examples, formulate a strategy, and then applying sophisticated automated filtering, like answer consistency or RIP, we are rapidly moving towards a future where LLMs can autonomously improve their own training data. It's a kind of closed-loop self-improvement.
Which pushes performance boundaries.
Right, pushing performance on tough benchmarks in both reasoning and instruction following, while dramatically reducing our reliance on that costly, sometimes inconsistent, often bottlenecked human annotation process.
A step towards more self-sufficient AI development.
It feels like a foundational step closer, yeah. Where models can essentially bootstrap their own intelligence in increasingly sophisticated ways.
So, thinking about the listeners, what does this all mean for you? Whether you're a seasoned researcher, a developer on the front lines, or just someone fascinated by the cutting edge of AI. If LLMs can now teach themselves to generate better, cleaner, demonstrably more effective training data than humans often can, and then filter it with this kind of precision, what are the next frontiers for data generation in AI?
Good question.
Could this approach fundamentally change the cost and the accessibility of building these advanced AI models? Could it democratize development beyond just the big labs with huge annotation budgets?
That's a huge potential implication, lowering the barrier to entry.
And what might that mean for the speed of future AI development,
Hmm.
especially in those highly specialized technical domains, science, engineering, where human expertise is just so scarce or incredibly hard to scale?
Faster progress in niche areas, perhaps?
Maybe. It's definitely something profound to think about until our next deep dive.